Hello. So I can see no one has joined, and I waited for like 10-15 minutes to start the session, but it's fine. So this is like week 11, and the course Technical Techniques of Material Characterization by Professor Shibayan Roy. I'm Jagrati. I'm a PhD scholar at IIT Gandhinagar, and I'm an PMR fellow, so I'm doing this for my TA duty, of course. Yeah, there's just only 1 week left, and after that, you have your exam. I hope you all do great in that, and I hope that the weekly sessions are helpful to you. Please let us know if you have any questions through the discussion forum. So, what I'll do is I'll just share the weekly content of week 11, and then I'll go through the assignments. Okay, so since there are none joined, I won't open up my PPT, and I don't think so. It would be an interactive session, but instead, I guess it would be a monologue from me. So I'll just go over from the lecture contents that have been shared, the material, and then following it, we'll just have a look at the assignments. Okay, I hope that's clear. I'll share my screen now. Mm, yes, here. So I went over this week and then I saw that it was something more specific to physical chemistry, that how scattering happens in an atom, what's the form factor for it, and then how do you do the calculations further. So you know that always when a scattering happens, it's not the curve. It's like there are two types of scattering that we saw previously when we were looking at the backscattered electrons. One was about the coherent scattering, another was about incoherent scattering. You can consider this both of them as elastic and inelastic scattering, where one type of scattering has more effect is more broadband, whereas the other one is more specific, is narrower band, is from one specific type. Whereas coherent scattering, when we say that, it's nothing but it's a constructive and destructive interferences of all the ones which are following in phase, and that's why it matches up to the energy, which is maximum. So it's not only from an isolated atom, but it's all the atoms which are making up one crystal. So for this case, if it's coherent scattering, you might also say that the scattering it's happening due to the atoms which are arranged in that spatial location in a periodic fashion, and the scattered radiation is severely limited to only certain directions. So we can say to some extent that it is isotropic. The directions of these beams are then fixed by Bragg's law, and then assuming that it specifies, we can nothing but consider that the intensity of the beam which is diffracted by the crystal is specific, nothing but it's a function of that atom position in that particular plane. Okay. Now, yeah, of course, there are some examples and some maths to be explained, but of course, we know that, okay, if you have a phase difference of something x, or let's say delta in this case, then what happens if you have a path difference of some 2 pi lambda? So, in that case, you derive this particular formula that's pi, the phase difference is delta by lambda times 2 pi, the path difference. So, only this thing. So, how much phase difference you have? So phase difference may be expressed in terms of angular measure as well as wavelengths. Two rays which are differing in path length by one whole wavelength lambda are said to have that they are in differences in the phase difference of 2 pi radians. So accordingly, so that's nothing but unitary method. You can compute that. And then for the functional coordinates, you can assume that, okay, for an atom which is placed at x, it will have x by a, for y by b, and z by c, which is equivalent to its unit replacements. So this relationship is nothing but applicable to a unit cell of any shape. And from there, if you apply Pythagoras or if you apply the cubic relationships, so following our phase relationships and part differences, you can directly compute it for all elements. Now, with respect to elements, your coordinates of h, k, and l will of course differ, and from there, your position might displace. Now, if you consider a wave which is passing through here, now what's a wave? Wave which is scattered by an atom of the unit cell will include the one which must be at origin should be added. So it will follow a complex relationship. So we know it can. So what we are looking at here is a sinusoidal wave with an amplitude with a phase difference to it, and now that will vary from different electron or different atoms to different atoms. Will have may differ in amplitude, but everything are in one phase. So phase remains the same there. So then all of them are can be coherently added, okay, where the phase difference is almost the same. Now, waves which are differing in amplitude, their phase may also be added by representing them as two different vectors whose length is equal to the amplitude of the wave, but then it is inclined by an x-axis at an angle that is equal to phase angle. So now we have an angle with respect to the x-axis, it is same, but what we have is like they differ in amplitude, so their phase can also be added, but the length of that particular wave is equivalent to the amplitude of it. So we can directly do it as like you can consider the parallelogram reconstruction law and you can add to them. Okay. Now if you have something like this, I don't know how it's that convenient for sciences student, but of course I know that people who have done the 11th, 12th and they have a little bit of maths, they'll be able to solve this. So here I is an imaginary number which is nothing but -1, how we express it, or square root of 1. So how you express it is like if you have an wave that's passing, that's a sine uh, 2 pi nu t, or it's like 2 pi lambda t, minus phi. So here they are taking negative of displacement. That wave can also be represented as a times the Euler's law. So this follows in Euler's law. That is nothing but e raised to ij or e raised to I phi is nothing but cos phi plus I sin phi. Now it's multiplied by amplitude, you multiply it by amplitude. Now you take the magnitude of it. How do you take the magnitude of it? It's nothing but square root of real component square plus your imaginary component square. So you take a magnitude of it, you essentially get only a square, because cos square plus sine square is 1. Okay, and square root of that is also 1. So here the amplitude that you essentially get is a. Now when following the structure factor, how do you compute the structure factor for it? So adding the scatter waves from each of the atom in a unit cell will require some addition of complex numbers which represent the amplitude and phase of each wave that we just saw now. Now the amplitude of each wave is given by an appropriate value of the atomic scattering factor, that's F, for the scattering atom considered, and the value of sine theta by lambda involved in the reflection, that's your Bragg's. Phase of each wave is then given in terms of HKL reflection and it's considered as UVW coordinates of it. That we know. The resultant wave, which is scattered by all the atom of the unit cell, is called as a structure factor because it describes how the atom arrangement given by the spatial locations of UVW for each atom and then affects the HKL scattered beam. So the structure factor is obtained by adding all of the waves together which are scattered by individual atoms. So this is our amplitude. You have your Bragg's equation, 2d sine theta is lambda. If you compute this component from it, so if you take just inverses, sine theta by lambda corresponds to 1 by 2d. And Prof has done some combinations, like if you want to add through all the atoms, you'll follow a summation from 1 to n function of the structure factor, and then followed by it you have your wave equation with respect to your spatial coordinates where HKL would be directly mapped to UVW. So that's HU, then that's KV, and then that's LW. Okay. Now here, so if in this case, when you see the F, the structure factor is linked to that nothing but your Euler's formula. So that is nothing but eventually your entire structure factor, which would be a function of the entire unit cell, but not of the one atom itself, would be a complex function. So that complex number will express everything, all amplitudes of all the waves which are scattered by individual atoms and the phases of the resultant wave. So if you take a magnitude of them, you'll get anything which is nothing but scattered by a single electron. Now, like the atomic structure factor, you also have delta F, which is magnitude of F, which is the ratio of the amplitudes. So you have ratio of amplitudes by entire unit cell divided by the which one that is scattered by one electron or one atom. So that you can represent it as n times the structure factor. Whereas what is your structure factor is nothing but an atom which scatters with with let's say z number of electrons in it divided by which is scattered by one electron in it. Okay, so now the intensity of the beam which is diffracted by atoms of the unit cell in any direction which is predicted by Bragg's is proportional to this square, obtained by multiplying this by its complex conjugate. So if you multiply f times conjugate of f, that's nothing but essentially the magnitude comes out to be f square. So they are saying that the intensity of that reflected beam, that diffracted beam, which we say from Bragg's law, in any particular direction, not in a specific isotropic direction, is proportional to the square of this particular ratio of amplitudes. Structure factor is an important relationship in extracrystallography since it permits a calculation of the intensity of this relationships from a knowledge of that specific locations that you have. Okay, so intensity is directly proportional to the square, which is nothing but the amplitude is a function of f and f conjugate. So if your f stands for, let's say, um, a times amplitude times cos plus I sine theta, cos theta plus I sine theta, then your f conjugate would be e times cos theta minus I sine theta. Okay, so that's just conjugate. Conjugating a terms means you just reverse this sign of your imaginary number. Okay, so I hope that's clear. Sorry, I don't have my tablet today so that I can write it, but I hope whatever I'm verbally telling would be clear to you. Okay, so now you can take some time to digest this particular structure. Then within like 5 minutes, I'll continue for the structure factor for a simple crystal structure, for a BCC1 and for a FCC1. Okay, so I guess these are just some useful relationships that you need to consider, and Prof has also written them very carefully. So we'll be able to go through them very quickly also. That's just 3 slides over there. So 5 minutes I'll give you, and then you can look over the others. Okay. Okay, so I guess that's almost time, and then we can directly go over to the structure factor calculations now. So we'll see the structure factor calculation for a simple crystal structure, for a base-centered crystal structure, for a body-centered one, and for a face-centered one. So to know about this, I hope you know the structure and how the relationships vary. Like it's equal in some cases. It's like following by one-third relationships, two-third relationships. So like I'm not from this exact background, but I do remember few of the things, and I would be able to help you through that. But if you have some core questions, you can always go ahead and post a discussion forum and address those questions to the prof directly, because he's the expert in this particular field. So he'll be able to solve your questions more appropriately. So this lectures, I'm very dicey about it. Not dicey, I guess that's the wrong word, but I'm not so sure that I would be able to have follow up through all entire things. But of course, this relationship following its maths, I know that. Okay, so let's look on it. So if you have your magnitude as nothing but sum of all the phasors which is scattered from all directions, and now you have this as nothing but from one unit cell, but not from one particular atomic structure. So it follows the amplitude times your phasor relationship. Now that is nothing but this particular equation that we just saw, 2 pi I, if you map it to these locations. Of course, you know through Euler's law. Now x stands for your particular angle, so that's cos x plus I sin x. Okay. Now when you do e power pi I, what it makes is there x is equals to pi. That means cos pi is always 0, whereas sin pi is always negative 1. Okay. So that you have negative 1 over here. So all odd numbers which are n pi will have always negative 1. Okay. Then you have 2 pi. So 2 pi sine is 0, whereas cos is 1. So then you have 1. Then you have n pi I. So that is nothing but negative 1 power I. Then again you have n pi I. So they are saying integer. So which is equals to the same thing. Now, okay. So now when it is nothing but an odd value. So if you're, okay. So since you know plus plus is plus, plus minus is minus, minus plus is minus, and minus minus is plus, right? All you have those odd and even relationships. If you have a function which is odd, so fn is equals to, what do you say? Fn is equals to, when fn is not equals to fn plus 1, assuming n is all even, and then you add a plus 1 to it. When it's an odd relationship, you always have a negative sign to it. Whereas when it's an even relationship, you have fn is equals to f of 2n. Of course, it depends on the type of the function. I guess I'm not explaining it properly, but yeah. So if you have an odd integer, it's always negative of that integer, given you see the function and how it evaluates. And then if you have an even integer, so ix plus negative ix. So how it will is like the one is 1, another one is also, so that comes out to be 2 cos x. Why? Now if you do this once, ix is this. Negative ix would be what? It would be cos x minus I sin x. So plus I sin x minus I sin x, both are cancelled. So you have 2 cos x. Okay. I guess it would be great if I had something writing, but I hope this particular slide is very clear to you, which are like very important relationships and there to remember. So yeah, we saw that structure factor which describes the waves which is scattered from the unit cell by together adding all the scattered waves which are differing in waves, differing in phase which are scattered by individual atoms in the unit cell. The phase difference in between the rays which are scattered by any two atoms is constant for a unit cell. And then you have a prediction by Bragg's law that all the atoms in A crystal are exactly in same phase, and so are the rays in B. But the two rays they have a definite phase difference in between them, which matters in between the definite or relative position of atom A and B in that particular unit cell. So of course, if one is like at U and another is like UA and UB, so there would be a phase or the relative position in the differences where they are placed in that particular unit cell. Okay. Now we have a simple structure, a simple crystal structure. So how many faces does it has, or how many points can you follow along it? So you have top four, then you have bottom four, right? So total you have eight of them. So if you want to find the structure, so 8 times for one, that's 1/8. So that's total one. Okay. So when you follow this particular relationship, now this is nothing but everything you'll have in terms of your 2 raised to n, your binary numbers. Okay. So when you have UVW, so it will start all the way from 2 raised to 0 to 2 raised to 4. Sorry, 3. Okay, so how many bits do you have? You have 3 bits over here because you have 2 raised to 3 is 8. Okay, so you start from 000, then you say 001, then you have 010, then you have 100. So how it follows is it follows as 4, 2, and 1. So your three integers 4, 2 and 1. So accordingly you make up this relationships, right? How many? So 0, 1, 1, that's how, what is that? That is 3. Then 1, 0, 0, that is 4. 1, 0, 1, that is 5. 1, 1, 0, that is 6. Sorry, did I miss any? And then that's 1, 1, 1. That's it. That's our 8. So these one relationship you can have over there. Now, if you want, so here, if you see, this is nothing but 8. 4. Sorry, that's not 8. How do you write it? 2 raised to 0, 2 raised to 1, and 2 raised to 2. So, oh, sorry, that's 4, 2, and 1. That's what we said now. 6. Oh, yes. Now you remember why it is 7 and it's not 8. Because we always have an integer bits from 0 to 2 raised to n minus 1. Okay, I hope that's clear because we are always starting from 0. So considering 0, we have total of 8, but we always have 7 there. Okay. Now these are extra diffraction patterns for the same. If you compute magnitude of it, then you solve for Bragg's. So for each and every location, it would have been different. So that is directly proportional to the square of their amplitude relationships that we just saw. Now for a base-centered crystal. Now what happens for a base-centered crystal? You have the faces, right? Now those are like 8, but you have something in the center also. So base-centered crystal. So you have 8. So 8 times 1 by 8 stands for the ones which are there in the corner. Plus you have 2 in the bases, the centered ones. So 2 times 1 by 2. So that corresponds to 1 plus 1 over here. That's total of 2 over there. Okay, so here also the relationships will follow in the same manner, but now you have only two relationships for both of them. So either you have 0, 0 or you have 1, 1. And for that case, you can see that h plus k is always an even number. Either you have odd or you have an even number. Okay. So now, if your cases are even, you have 1 plus 1, that's 2n. Whereas the cases are odd, so 1 would be negative 1. So you have 1 minus 1, that's 0. Okay. And the same thing for this also. So you see that where the 1 is lying to and its structure factor, you directly add and subtract it. It's that simple. Okay. So you don't need to remember also that. Okay, next one is for BCC crystal, FCC crystal, and an NaCl crystal. NaCl is there in the assignment questions also, so I guess solving this would be easier, will help you too. So I guess there are way too many contents today. So what we'll do is like, since it's already almost 11, but we have like, we just started like after 10:30, not 10:30, 10:20ish, because I was looking if there are many people. So I'll go over two more lectures now, and then after I guess we can stop and look at the assignment so that we would have sufficient time to go over the solutions also. So 5 minutes here and then the next one. Okay, that's also pretty much simple. So we can have a look at it also. Okay. Okay, so that's like almost pretty much 5 minutes. So we'll go over body-centered crystal now, the face-centered ones and NaCl. So we saw here how the structure and how the numbers, how the calculations vary. So it's just that simple. Just need to remember how the spatial locations will vary for them for each of the given different configurations. Okay. So now it's body centered one. So what follows in I guess that one was also the same one. Body so that's base centered. Okay. Now you have a body centered. So what works in body centered? Now you no longer have in edges. You don't have in the base centers, but you have in the center of your body where the atoms are split into halves. So you have a complete sphere that's forming inside. So that's your body centered crystal structure. So how follows for it is like it would only have one particular spatial location. That's nothing but to the center of it, give it as half of half, and then it starts from zero. So now how will it translate? So then if you look at these, so of course here also you have some relationships in between odd and even that we looked previously. If it's even, you have 1 plus 1, or you have a negative 1 followed by it. The amplitude is also proportional to the amplitude squares. But there's one thing over here that now you have two relationships here. One starts from 0 0 0, whereas the another one is like limited till x by a, your y by b, and this one that's z by c. So followed by all is nothing but your halves. So now this relationships, when you express this, will also have two terms in there. So you have two different phasors there. So you have e pi I times 0, so that's your structure, x distance that you are specifying there, whereas the other ones will have nothing but h by 2, k by 2, and l by 2. So if you have all ABCs as 2. Now from there, you follow the equation. So 1 is nothing but here will have some relationship, whereas this is entirely 1 because this is almost like e raised to 0. So what's e raised to 0? Sine 0 is 0, cos 0 is 1. So that is nothing but 1. And then followed by this, you have e pi I, whereas pi times all integer numbers. So that is nothing but e raised to pi I is negative 1. So negative 1 raised to n. So you always have this as negative 1, the amplitudes, whereas the magnitudes can be the square of it. If you take the magnitude, it would be a function of the square of your f value. So that's your structure factor. So then if you have a BCC crystal structure, if you follow for it, this is nothing but based on the elements that you're trying to see over here. For okay, so let's see how it goes. So there are different ones. So 110, then you have this 200. So you see these relationships 211. So I don't know how many numbers they are considering there, but you have also 321 in that case. How do you write these? So this one's so it is no longer following that three integer decimal places or three bits that you have, whereas it's just giving you numbers based on the spatial locations that it's lying on. Okay, so this is your 4, then you have 6, and then you have your 7. So that's nothing but 8. Whereas, so these numbers, how it follows for which particular structure style, whereas the other ones are body centered ones, so which way to that particular base, so it will follow. So here, forbidden reflection. Okay, so if it's order, you see that it won't follow this 200, 220, 100, 111, and 110. So if you have those numbers in there, it won't follow those ones, whereas for the other structure, it will follow them. Okay, so now next one is also with respect to the body centered and the base centered. So you know now that way, what's the actual difference in between the body and base centered? But there would always be this 100. So that's nothing but 4, which is falling in both of them. So you just have to differentiate that which one follows where and the differences in between them. Then you have a face centered. So face centered will of course have the top 4, the bottom 4. You have the two body centered ones, and then you have the 4. So you have 2 in this faces. Let's say the left the front faces, whereas 2 in this faces. So you have total of 4 in these particular faces, and then later you had 4 4 8, and then you had this 2. So 10, and then you have this 4. So that's 14 in total. So now how do you see them? 8 were there in this. So 8 times 1 by 8 for each. Then you have 6. So where does that 6 comes from? So it comes from the faces that you have. So you have 2 here, and 2 here, all centered. So those are like 6. And then for each stands half. So you have 3. So 1 plus 3, that's 4. Okay. So at first we were just seeing how many crystals and at which particular planes would they be. Now we'll be looking at how many numbers are at the centers, are at the corners. So then you have how do you call it as you have a configuration which is base centered, face centered, and body centered. Okay, I hope that's clear. So then accordingly you follow these relationships. I hope that is clear now from there. So you just given this factor, so you have 8 times of this, then you have 6 here, and then so that's it. That many configuration you only have. So for this 8 times 1 by 8, you will have total 8 of them. So that starts from 000, whereas for the other one you have 3 of them. So you have these 3 relationships for it. Now following it, you do even and odd ones, you write it down. So this cases will also have 3 cases here. So first one is nothing but pi I that we know. Second one would be half of it, here this one. The next one would be half of it. The next one will be minus of it. Okay, so following it, you have these all 3 relationships based on the numbers. You just calculate the spatial locations, how it would be even, how it follows odd, and then from there you know the relationship for it, right? So it would be 4 times f. So if you square it, it would be 16 f squares. Okay, that's it. Then, okay, so then you need to see that, okay, whether the particular given configuration is face center or body centered, so that you know till now, and then how it's proportional to it, so which particular element it follows along. So you just have this graphs, and from this particular configuration, if you know, you can directly compute for it or just given an idea for it. So this is nothing but a table summarizing for all relationships. If you have a simple all, then reflections are absent of it in that case. Then you have a base centered one. What happens in that case is it's mixed. Body centered one, you have all as even, whereas you'll have reflections as odd. Whereas the face centered one, if they are possible, would be unmixed. Whereas if they are absent, would be the ones which are mixed. Okay. Missing diamond cubic structure has face, but it contains 8. So all the reflections present have unmixed are missing. Then you have the fact that they are okay, so this is fine. This is if there are details, let's just have a look at them so that we don't miss it. The fact that only reflections present have unmixed indices proves that the lattice is face centered, while the extra missing are a clue that the actual arrangement in this atom. Okay, I guess so. That's it. Then there's next one, so that follows for an NaCl crystal and for in real specimens. Okay. So here, okay, he has explained how it's missing in those cases. For the simple one, for the base one, for the body centered one, for the face centered one, how it's missing and not. Okay, so this is simple relationships. Okay, now you have sodium and then you have chlorine. Now how sodium follows is like 000. So it's a simple one. Whereas chlorine, it follows last one, what we saw just now, face centered one. So you follow for all of them. So half of half. So you do the relationships, which particular combinations are possible in this cases, and then you go on write the equation for it. That's it. What else do we have here? Hmm. The first term corresponds to the phase centering translations that you know till now. And the second factor contains the terms that describe the basis of the unit cell. That's also fine. And okay, so it's even and odd. That also you know that. Okay, so doing these terms like cos theta plus I sin theta, or if you do something as so that x can be flipped in between that first and second term. So it can either be sodium plus chloride, it can be chloride plus sodium, or sodium minus chloride, or chloride minus sodium. So it's always interconvertible if you have these relationships. Okay. Patterns that also know. So there are 6 factors now which affect the relative intensity of the diffraction lines on a powdered spectrum. You have your structure factor, F, that's a function of the amplitude square. Then you have a multiplicity factor, you have a temperature, you have polarization factor, the Lorentz factor, and then you have absorption factor. So these are like how your intensity matters and how it differs. So it must always begin with a structure factor. For that, you should know that this particular element follows which type of structure. And if you are from a chemistry or physical chemistry type of background, it should be very easy for you to know these terms. The remainder of the calculation varies with the particular diffraction of the method involved. And for this specific method, I'm not sure what that method is, but the calculations are so difficult that they are rarely made. Okay, it's fine. Then you have the rotating crystal and powder methods are somewhat similar, and in that the monochromatic radiation is being used. So then they have explained us what's a multiplicative factor. So that's nothing but something similar to your amplitude term. So how you have A. So relative proportion of the planes contributing to the same reflection enters the intensity equation as a multiplicity factor. It's defined as the number of different planes have the same spacing, the structure factor. The permutation possible for this particular position are like plus minus ones for a plane, so we'll have the same distance and the same magnitude relationships. If you have planars with some Miller indices as this, so these Miller indices are nothing but your 3-bit integer indices are counted separately as different planes, and the factor for this ones for this is 8. Yeah, that you know that. For if you have this one, so if you consider a factor for this particular plane of this, that is 6, whereas the other one is nothing but 8th plane. So now till now, I hope you know those. And if you have a crystal like this one, so you have a face centered or a body centered one, you have all the 100 or 010 or 001 as equal to all of those cases. Okay. So I guess that's it. We planned on doing till this particular lecture, and then you have 10 more slides. Is that just 10 more slides? Let's have a look on it. So it's multiplicity factor. Okay, it's fine. Then you have, yeah, if you have a body-centered one, the factor, the plane, this one, that's 4, is reduced to 4, and the value of this, that's nothing but planes to 2. Okay, then you have two relationships there. Either it's 0 or 1. Okay, so you have third one not equal to another. Okay. So from this one till this one, this particular big of a table. So I can only help you till the part where you have 3 bits integer, or you have something as similar to that of how do you compute it. This terms if you have something similar to your what do you say? Um, your Euler's function. So I can help to that part, but I'm not so confident with this phenomenon right here. So how after your diffraction or which particular planes will that follow in? So for that elemental ones, I guess you just need to refer to the table or particular like solid chemistry or those kind of books where you can get these things very easily. Okay, so now for temperature, we know that it's always affected by intensity and in the atoms which are located, whereas all and every atom will undergo vibration by the mean position, even at absolute points, and the amplitude of the vibration will increase as the temperature increases. Now, in aluminum at room temperature, they have said that an average displacement is about like 0.17 angstrom, which is like 6% of the closest distance to the mean atom. And then if you have increased thermal vibration as a result of increased temperature, causing changes in the phase spacing as d and therefore in 2 theta positions of the diffraction lines. So what do you have with respect to the path difference? That's always 2 theta by d. Okay. And then if the positions of one or more lines are measured as a function of the temperature, the thermal expansion can also be determined as a function of your X-ray diffraction. The intensity decreases where the intensity of the scattering lines increases, in between the lines increases. So if you have more spacing, the intensity of diffraction will decrease in those cases. Then if you reinforce them at Bragg's angle at various lines, it may not be that perfect as for a crystal with fixed number of atoms. But if you say that if U is a displacement for a mean position, then it would be imperfect if you have a ratio as U by D. It will increase as your temperature increases. So that's it. Okay. And yeah, this factor also. So your temperature is introduced as e raised to negative 2m, which is a number calculated intensity allowed to multiply as the thermal vibration of atoms increases. So qualitatively, if you say as this decreases, then so this particular term will decrease as your 2 theta increases. Why so? Because if you have cos theta plus I sine 2 theta, then as your angle increases, your terms reduce in orders. Right, so number decreases. So hence qualitatively your magnitude will also decrease in that case. I'm not saying either it's positive or negative. I'm just saying the magnitude will decrease. Okay. So I guess that's it for this entire one. We were able to complete the entire lecture 11, week 11 over here. If you have any questions or doubts, you can just note down in the discussion forum, given if like I can see no one has joined till now. So then I'll wait for 5 minutes and then we can always go to the solutions and then look at the week 11 solution from last year. Okay. Sorry, that took some time. I had some hiccups here. Okay, so now I'll go to the last week's solution content and then that's it for this one. Okay. So now week 11. Okay. How do I move it from one place to another? Okay, that's great. Okay. Yeah. So a missing peak in the XRD pattern in an otherwise expected position will indicate what? If its systematic absence is due to a specific symmetry and incorrect choice of radiation wavelength for the given experiment, or a defect in the lattice, or all of the above. So we know if anything's absent, that also affects it. Your pattern's missing peak, whereas and if you're not exciting it with that particular specific wavelength that the element is supposed to get excited into, that also affects, and then the defect in the crystal lattice also affects. Okay, so these all effects will entirely break your symmetry and hence all of the above. Then multiplicity factor for this and these planes in this are what? So we saw this previously. This is 6 and this is 8. Okay, that's pretty much it. So you should know the 3-bit integers till now. Then Bragg's law relates the diffraction angle theta and the wavelength this. So how it relates? It's 2d sine theta by lambda, right? So it tells you the distance in between the adjacent atoms in the crystal, or the distance in between the adjacent planes, or is it the number of atoms? It's not number of atoms, we know that. It's not even the atomic number of the atoms, that also we know that. So Bragg's law essentially tells us something about the constructive interference, right? Where the part difference is nothing but an integer interval of the distance which is scattered in between the adjacent planes of the wave. Okay, so that follows your option B, which says that in between the adjacent planes. So you just notice the keywords there. So Bragg's law describes the condition for constructive interference, right, which occurs when the path difference between the waves which are scattered from adjacent planes is an integer multiple of that of the wavelength, okay, n lambda. So 2d sine theta is n lambda basically. Then you have a structure factor, which is primarily determined by what? So a structure factor is the total number of atoms or the type of atoms or the relative positions or the wavelength. So we always know it's function of your relative positions in your atom within the unit cell. So ones which are scattered by specific from through specific crystallographic planes, it is HKL, and which are defined in that particular unit space or spatial space as VW. Okay. Then you have in a body-centered cubic crystal, which of the reflections would be absent, systematically absent. So you have this option of 1, 1, 1. Because we saw 1, 1, 0 is there, then you have 2, 2, 0 and 2, 2, 0, 0. So in this case, it represents the ones which are nothing but are odd. So these odd ones are directly absent from there. It's even essentially, right? Then in a crystal with simple cubic symmetry, the introduction of additional atoms of different element in either face or body would do what? So would always eliminate some reflections or introduce or always increase the intensity or potentially decrease the intensity of certain reflections. So that we know of certain reflections. Now these certain reflections can either be the even ones, can be the odd ones. So in this case, it will always be an odd one, right? So this could lead, how it explains is the additional atoms from different element will introduce new scattering centers that will alter the phase relationship of the scattered rays. So this option is somewhat that vague. It's not explaining the exact phenomena there. This could lead to reduced constructive interference and thus may decreases. So it's exactly dependent on your entire logic there. Now for a given set of planes, if you have HKL, the multiplicity factor will follow what? So number of planes with same Miller indices, I don't think so. Then you have something as number of planes with the same spacing and structure factor, or you have same spacing regardless of structure factor, whereas you have always equals to 1. So always equals to 1 follows for only face the simple one, whereas this follows the spacing and the structure factor, right? So the factor accounts for the equivalent planes which are contributed, like which are placed at equal spacing, that will contribute to the same reflection from them. And so that the spacing is identical and hence the scattering property, the structure factor will also be there, which is magnitude of the amplitudes there, ratio of amplitudes. Then you have which is not directly affect, which won't directly affect the intensity of the beam. So we saw polarization factor does, temperature does, Lorentz does, but the lattice one doesn't. So that's it. So simple terms like this will also be asked. That's why I was focusing that on more. So you also need some, it's like, of course, you need to understand the phenomena there, but if you miss one of them, your one MCQ is directly done.
Okay. Now in a tetragonal crystal system, this particular is what? So you have this as 4. So you know your 3-bit digit system, or you know something about the tetragonal crystal, you can directly solve for it. Right? It's tetragonal. The answer follows as 4 because you always have that as 4. Right? Now, due to thermal vibration, the average displacement of an atom from its mean position will do what? So, if you have thermal vibrations, the displacement from the atom from its mean position will eventually increase with increasing temperature. As temperature increases, it would be more displaced towards the other point. So, as temperature increases, the atom will have more kinetic energy. That is how it will be displaced to a larger distance, half mv square. So, as velocity increases, the displacement will also increase and it will be move toward larger amplitudes of vibration and thus a greater displacement from its main position. Okay, so that's directly from kinetics there. Increasing temperature affects the extra diffraction pattern of a crystal by what? So if your temperature increases, what happens? Does your intensity of your diffraction peak increase or does it decrease while increasing the background scattering or shifting to a higher one, shifting to a lower one? So in this case, it decreases the intensity of the diffraction peak while increasing the background scattering. Okay. Which of the following crystal structure has a structure factor which is independent of this one? Structure factor independent of this HKL. That's a basic one. It's a simple cubic. For base-centered structure, so what's your base? You have all 8 and then you have the center 2 also for the bases. The 2 effective atoms per unit cell are located at which locations? So these are nothing but 0, 0, 0 and half of 0. Okay, so these are nothing but all at the corners and then you have 2 at the base center positions. So effective number of atoms is 2 in that case, 0, 0 plus 2. Okay, so they are located in this case is 1 plus 1. Now, face-centered structures shows forbidden reflection when. So we saw that when they are mixed. Okay, that is clear. And then your NaCl crystal, so Na follows a simple one, whereas chloride follows a body one. So these are what? For planes having, if it's mixed, unmixed, mixed, unmixed. So you always know the answer is mixed over here because they will occupy alternate positions and corners. So one occupies the corners, another occupies the face. Sorry, I said it wrong as body. It was face. So while these are mixed, the X-rays are exactly out of phase by half a wavelength, and the out of phase scattering will lead to complete destructive interference, causing no observable peak, diffraction peak for those particular planes. So when they are mixed there. So I guess we are done here for this particular week. I'll stay in the session for 5 more minutes and we'll see if someone joins. If they have any questions, I'll be happy to help them or else we can close off for this session. Okay. Okay, I guess I don't see anyone joining till now, so I'll be closing the session here. And thanks for joining. Sorry, thanks for having a look, and I guess that's it from my end. Thank you.